I'm A.L. Goldman. I teach physics at El Camino College. This far in the course, we have only studied the free fall motion of an object near the Earth's surface, moving either straight up or straight down. We have learned that if a free-falling object near the Earth's surface is moving up, it is losing speed at 9.8 meters per second. And if a free-falling object near the Earth's surface is moving down, it is gaining speed at 9.8 meters per second. In this video, we're going to consider the motion of a free-falling object which is launched at an angle which is oblique to the horizontal. So, for example, we can think of a cannon here at the origin, which launches a cannonball into an angle which is oblique to the x-axis. And you can see that as that cannonball, which we will assume to be free-falling, traces out its trajectory, it will have motion along the horizontal, but also motion along the vertical. And we would like to understand both the horizontal motion and the vertical motion of this free-falling projectile. Now, in order to do this, we're going to imagine that the object carries with it two flashlights. One flashlight is a blue flashlight, which is always pointed directly downward, directly at the x-axis. And that blue flashlight makes a spot of blue light which exactly tracks the horizontal motion of the object. Let's say that that object also carries with it a pink flashlight. That pink flashlight always points exactly horizontally. And because it always points exactly horizontally, it makes a spot of pink light. And that spot of pink light will always exactly track the vertical motion of the object. Now, I claim that if we can figure out the acceleration of that blue spot, which exactly tracks the horizontal motion, and we can also figure out the acceleration of that pink spot, which exactly tracks the vertical motion, we can put those together, and then from that, we will know everything we need to know to solve problems involving free-falling projectiles moving in two dimensions. Okay? So we're going to do two experiments. One experiment is going to help us figure out the acceleration of that blue spot, which tracks the horizontal motion. And the second experiment will help us figure out the acceleration of that pink spot, which tracks the vertical motion. So for our first experiment, we have a cart, and in the cart we have a shaft, and in that shaft is a spring, which you can't see, but I can take this ball, I can drop it into the shaft, I can push down on the ball so that I can press the spring, and now the spring is loaded. Then when I use the remote control here, the spring releases, the ball is projected straight up and comes right back down into the shaft. And I'm going to roll the cart along the table. And as the cart is rolling along the table, I'm going to hit the button on the remote control, and that will project the ball into the air. After that ball is projected into the air, there are three things that can happen, right? One thing that can happen is that the ball's projected into the air and ends up landing behind the shaft. A second thing that can happen is that the ball is projected into the air, goes back into the shaft, and then a third thing that can happen is that the ball is projected into the air and lands ahead of the shaft. What's actually going to happen when we run the experiment? And how about that? The ball went right back into the shaft. I claim that the reason the ball was able to find its way back into the shaft is that the ball was in fact directly above the shaft the entire time. So I'm going to do the experiment again. Imagine that the ball has that blue flashlight that always points straight down that we were talking about before. Think about that blue spot tracking the motion of the ball. We saw the ball get launched out of the shaft. It went back in, and I hope you were following the motion of the shaft that time. See if you can describe to yourself what that blue spot is actually doing. And I hope you can agree that the shaft was moving along at constant velocity, and that blue flashlight is pointing into the bottom of the shaft, then that blue spot is moving along at constant velocity as well. Then what is the acceleration of that blue spot? It's 0. All right, so we are halfway there. We have now done an experiment which tells us that the acceleration of the blue spot is 0. Now we're going to do an experiment which will tell us about the acceleration of the pink spot, which tracks the motion of the projectile in the vertical. All right, so in this experiment, I have a metal rod here, and one end of the metal rod slightly overhangs the end of this apparatus. On that end of the metal rod, I'm going to thread a metal ball that has a hole in it. Now at the other end of the metal rod here, there's a little well in the base. So into that well, I'm going to put a second metal ball. Now when I push this button here, what's going to happen is that the metal rod is going to suddenly shift over. And when the metal rod suddenly shifts over, this ball here will no longer be supported, so it's going to drop straight down. This ball over here gets hit by the metal rod and is projected out horizontally. So at the same moment, one ball begins to drop straight down, and the other ball is projected horizontally. So here's the question for you. Which ball is going to hit the table first? Does the ball drop straight down hit the table first? Does the ball projected horizontally hit the table first? Or do the two balls hit the table simultaneously? So here I'd invite you to pause the video and see if you can predict what's going to happen in the experiment. Here we go. So I hope we can agree that both balls hit the table simultaneously. I claim here that the reason the two balls were able to hit the table simultaneously is because both balls were exactly at the same height as each other the entire time. So I'm going to run the demonstration again. Now I want to think about this in terms of that pink flashlight. Well, can you see that if the balls were always at the same height as each other, that pink flashlight would have been pointing directly at the ball which was just dropping vertically. If that pink spot was always directly on this ball, what was the motion of the pink spot? Well, the motion of the pink spot would have been the same as the motion of the ball that was just dropping vertically. Okay, now what is the motion of the ball that was just dropping vertically? Well, it was accelerating down at 9.8 meters per second per second. Then the pink spot as well must have been accelerating down at 9.8 meters per second per second. So now we have the second part of our answer. We now know that the acceleration of the pink spot along the y-axis is minus 9.8 meters per second, exactly like a ball that had simply been thrown straight up or dropped straight down. So now we know everything we need to know about the motion of a free-falling projectile. Right? We know if the free-falling projectile carries those two flashlights with it, then that blue spot tracking the horizontal motion has an acceleration of 0, or in other words, it's moving at a constant velocity. And that pink spot tracking the vertical motion is accelerating down at 9.8 meters per second. And from those two pieces of information, we can solve any problems we want to solve involving projectile motion. And in the next video, I'm going to start by writing out all of the equations that we're going to need to solve problems involving free-falling projectiles. But those equations are going to be based simply on the idea that that blue spot has an acceleration of 0, or in other words, constant velocity, and that the pink spot is accelerating down at 9.8 meters per second. Thank you for watching. I'll see you next time.